Hello and welcome to this video. So this video is part of the class Introduction to Artificial Intelligence and Machine Learning for Engineers. So in this video, what we are going to talk about is to talk about image analysis and convolutional neural networks, short for CNN. So, so far all the lectures we have seen when we talked about artificial neural network, about polynomial regression, about lasso, etc. So in this case, for all the cases of supervised machine learning that we had a case where the input was a series of numbers. So the different features were some numbers, different features x1, x2, where each value of x can be a given number, a real number. And you have a given output, which is either a number or a class number, depending on whether you have a regression or a classification problems. So now the question is, if the features that you're trying to use as input to make a prediction is not a series of numbers, but actually a picture. If you have a picture in front of you and you want to analyze this picture to predict something, you want to, for example, predict if there is a given person on this picture. You want to predict if you take a picture of you, is it your face or not, so that it should unlock your phone or not. Or you want to detect if there is a certain object on this picture. Or you want to determine for a given person what is the emotion of this person just by looking at the features of the face of this person. So in this case, the input of the model will be not some numbers, but now a picture with made of certain pixels, and each pixel can have different colors, and this is what is going to be the input of your model. And then your model at the end, as an output, will give you a prediction of something, if there is a certain object on this picture or not. So this types of problem, which is related to image analysis, is something that is very important, especially in civil engineering, because this is everything that relates to analyzing pictures and making some predictions based on pictures. So a typical example of when these types of problem might be relevant, one of very important application today of image analysis and convolutional neural network is self-driving cars, in the sense that when you have the car that is driving, the car is constantly recording its surrounding in front of the car, behind the car, and on the edges as well. So you have some cameras, and those cameras are going to be recording live the environment of the car. And for the car to be able to drive from point A to point B in a safe condition, the car needs to be able to analyze its environment based on what it sees on the camera, which means that it needs, based on the video that is provided by the camera, the car needs to be able to recognize if there is another car somewhere else in the vicinity of this car, so that it should be careful of avoiding any collision with another car. It should be, of course, very careful and aware of whether there is a potential pedestrian or person walking on the street. Then it needs to make sure the car will be able to detect that there is a person on the picture, and that the car should stop or change its trajectory to avoid colliding with the person. Another thing is that the car needs to be able to see the signalization, like the fire, the traffic light, or the different signs for traffic, like whether there is a stop sign or those kind of things. So those are all things that the car is not aware of this information. The only thing that the car has access to is a video that is a live video that is offered by some cameras, and the car needs to be able to analyze in real time this video and to detect relevant patterns within this video, patterns suggesting the existence of another car, of a pedestrian, of a traffic sign, or different kind of traffic light, different kind of information that will then inform how the car should adjust its speed or adjust its trajectory. So that's one thing that is a very important application of image analysis. And for this, the way you can analyze those images and make some predictions based on the analysis of those pictures is by using convolutional neural network. Another application is analysis of satellite pictures. So if you have a lot of pictures offered by satellites, you have potentially millions of those pictures, and you cannot have a human looking at them one by one to detect whether there is any kind of signature of a potential landslide or anything like this, or any other kind of analysis that you may want to do by looking at satellite pictures. And so in this case, it's going to be very useful to train a CNN model to be able to automate the task that the human would otherwise be needed to do. Another application is everything that is revolving around social networks and being able to detect the identity of the person feature that are featured on a given pictures. Another application of this is using camera or pictures of you to unlock your phone. So to detect whether it is you or not on the pictures, to decide whether your phone should be unlocked or not. So all those things rely on the ability of collecting a lot of pixels through taking a pictures with a camera, and based on those pixels, making some predictions, analyzing the values, the colors or the luminosity of those pixels, and being able, based on this, to predict a given output. So the typical problem that you want to achieve in this case is as follow. You have a given picture. So you have a given picture in front of you, and you want to use this picture to detect whether this picture contains a given pattern, given object, or in this case, whether this picture contains a cat or no cat. So in this case, for a human, this is an activity that is pretty easy to do. It's going to be pretty easy for even a kid can quickly look at this image and say, yes, there is something that looks remotely like a cat. But for a computer, that's a very complicated task, because it doesn't know what are the rules of what makes a cat, or like how to differentiate a cat from a dog. And so that's one thing that makes it pretty complicated. And the second thing that makes it even more challenging is that when you see this picture, you can clearly see that there is a cute animal like this, that with you can see the face, and this face is has the shape of a circle, and this circle is located at the bottom right of the picture. But the computer doesn't see that, because for the computer, what an image is just going to be a collection of pixels. So you will have this picture is going to be divided into a series of a lot of pixels. And for each pixels, the information that the computer will have is, if it's a black and white picture, then each pixel will be associated with a level of gray, where the level of gray can go either between 0 and 1, or between 0 to a given arbitrary value. So you have the level of gray will be encoded as a number. Or if it's a colored picture, then the way colored pictures are stored and can be analyzed by a computer is that for each pixel you have a free channel. You have the RGB channel, where R stands for red, G is for green, and B is for blue. So for each pixel you have three values that tell you the level of red, the level of green, and the level of blue. And based on the values of those three channels, so those are three different channels, then the picture will have any kind of arbitrary color. So in this case, what the computer will see is, for each of the pixels, for example, if this is, let's say this is a 1000 by 1000 pixel, then what the computer will see is so 1000 by 1000 pixels, and for each of those pixels there will be three information, which is the level of red, the level of green, the level of blue. So altogether, what you will have is, what the computer will see is just 3 million data points, which corresponds to each of the pixels and each of the 3 channels for each pixel. So this is what the computer will see, just a collection of those 3 millions values. And starting from those 3 million values and converting it into pictures and the way human can interpret pictures, in the sense that as human we can easily see patterns within pictures, we can see shapes that are cohesive, we can detect lines, we can detect circles, squares, all those things that are very easy for human. Like you can easily detect that there is an object on this picture, and you can differentiate this object from the background. This is something that is very easy to do for humans, but for computers that's something that is very challenging, because all they see is all those jam of pixels, all those collections of pixels, and trying to making sense of all those pixels is something that is a very challenging task for computers. So one possible idea on how to make sense of this, it would be to use all those pixels and use those pixels as input for example, an artificial neural network. So the way it would look like is that since here you have 3,000 pictures, then it means that you have 3 million pictures. It means that you would have 3 million features. So where each pixel, each channel of each pixel would be one feature. So then you would have all your features x1, x2, x3, etc. up to x 3 million. So those are your 3 million inputs. And one option would be to train an artificial neural network where you start with those 3 million input neurons. Then they would be connected to some hidden layer neurons. So for example, let's assume that you would use, let's say, 1,000 hidden layer neurons. So all those features would be connected to the neurons like this, and then at the end you would get all those hidden neurons would be connected to the output neuron, and this output neuron would be the output of the model. And for example, if you choose the activation function so that the output will be necessarily between 0 and 1, and you can train your model so that when y is larger than 0.5, then it suggests that a cat has been detected, and when y is lower than 0.5, then it suggests that unfortunately there is no cat. So this is one possible option, and that can work for certain cases, especially when you have very small images, like maybe 10 by 10 images. But it cannot work. There's no chance that this can work for regular pictures, which are typically made of at least a few millions of pixels. Why? Because here, if you train this model as an artificial neural network, then it means that you will have to find the values for the weight corresponding to each of those connections. Here, you will need to add a bias for each of the neurons. So that will give you like a very, very high number of parameters. For example, even if you only look at the connection between the input neurons and the hidden layer neurons. So here you have 3 million input layers, neurons, sorry, and then you have 1,000 neurons in the hidden layer. So the total number of weights that you will get, the total number of weights that you will need to fix for each of those connections will be the number of input neurons times the number of neurons in the hidden layer, which in this case would give you 3 billion weights that needs to be parameterized. You need to find the value for each of those 3 billion weights, which means that ideally you need to have something like 3 billion pictures that you can use, 3 billion pictures of cats and 3 billion pictures of no cats, so that you can properly train the model, so that you can find the right values for each of those 3 billions of weights. So in this case, that cannot work in practice. There's just too many parameters to fix. So it's very likely your model will be overfitted and that you won't have enough pictures in your training set to train this model on how to recognize a cat. Training a model on how to recognize a cat here would mean to train the model to get the right, to fix the right value for all the weights W1, W2, W up to all those 3 billion weights. Those 3 billion weights needs to be optimized in order for the model to start being able to detect whether there is a cat or not. So it's just too much weights, too many parameters that needs to be fixed, and so that's why this option is not practical in real life, because just there is too much information embedded in pictures, which means that there is just too much parameters that needs to be fixed. So here the key problem in artificial neural network is that they are fully connected. What does it mean to be fully connected? It means that each neurons in the input is going to be connected to all the neurons in the hidden layer, and that same thing, like the output neurons will be connected to all the neurons in the hidden layer. So there is every neuron in one layer is going to be connected to all the neurons in the next layer and all the neurons in the previous layers. It's fully connected, which means that there is a lot of weights that needs to be parameterized for each of those predictions. So if we want to be able to train a model that is able to deal with the amount of information that is stored in pictures, we cannot use a fully connected model. We need to use another type of model, which is going to be the convolutional neural network model, which is not fully connected. And that's going to be very important to decrease the number of parameters. It's a very key thing that the network will not be fully connected to decrease the number of parameters that needs to be trained. And this is what makes it possible to train those convolutional neural network, and to also to make sure that they are not overfitted by decreasing the number of parameters that needs to be trained. There's another problem if you wanted to use this approach of using an artificial neural network to predict whether there is a cat or not in this picture, is that in this case the cat is at the bottom right, but the cat can be anywhere. Like if you translate the cat somewhere else in these pictures, the model needs to be able to detect that there is a cat, even though maybe the cat will not be located at the same pixels or in the same position in the pictures. So that's a problem with if you use a conventional artificial neural network, a traditional artificial neural network, is that you would need to train the model or to fix the weight of the model several times to detect whether the cat is located on picture 1, or if it's on the pixel 1, or maybe the cat is going to be located at picture 2, or maybe the cat will be located within a range of pictures here, or maybe a range of pixels here, maybe the cat might be there, etc. So which means that you will need to have some weights that will be able to capture whether the value of the pixels suggests that there is a cat here or not. And you will need to do this several times, a high number of times, because in this case, the input of the model are the pixels directly. So you need, in this case, you would need to be able to detect, is the cat located in around those pixels, or is the cat located around those pixels or around those pixels, which means that you will need to keep doing the same thing over and over for all the pixels. So clearly that's not a good strategy, because you will need to use the same weights for several features, for several collection of pixels, you will need to keep doing over and over the same operation to detect whether there is a cat located here or located here. So it would be much more efficient to have a model that does not depend on where the cat is located, and that a model that would give you the same answer independently of where the cat is located. And that's going to be another advantage of convolutional neural network, is that they can deal with objects that are moving throughout the pictures, and still be able to detect this object without having to redefine the way to detect this pattern several times. You just need to define this pattern once, and then it's going to be able to look for these patterns everywhere through the picture without having to redefine it several times based on where this object is located on the picture. So first, let me show you what will be the typical overall architecture of a convolutional neural network, or CNN. And then we are going to come back in more details on each of the different operations that you have between the input and the output of this model. So for a CNN model, what you start with is a given image. So you start with a given image, which is typically a grid, a 2D grid, a two-dimensional grids that is made of pixels. And each pixel can have a different value based on the color or the grayscale of each of those pixels. Then this image is going to be transformed into another grid, potentially with a different size, and this grid is going to be transformed into another grid. Potentially those grids can start to be three-dimensional instead of being two-dimensional. We will come back on these points. And then at some point, what you will do is that you will transform this grid into a single vector. So you will take the values of all those pixels one by one, and you will just flatten them like this into a single vector. And then each of the elements of this vector will become the input of a traditional artificial neural network. So you will have some neurons like this, and each of the neurons will be connected to the neurons in the hidden layer, and then those will be connected to the output neuron, and this is what is going to be the output of the model. So for example, in this case, if y is larger than 0.5, then it means that the network will have detected a cat in the input image, and if y is lower than 0.5, then it means that there is no cat. So the way you can go from the initial image up to the final output of this model is you have quite a few steps. So you have all those operations here that are going to be like the specificity of the CNN. So here you will have different layers of operations that you are going to apply to your image to transform it, to detect certain features, certain patterns within your image. So this is the step where you will try to detect some objects, some shapes, some edges, some lines, some, for example, if you detect that there is a circle, this circle might indicate that this is the face of a cat. If you detect some lines, maybe this is gonna be the mustache of the cat, or like those kind of patterns that can be useful in detecting whether there is a cat here or not. So this is what will be accomplished in those different layers. It's going to be trying to detect certain geometrical features within the input image. Then at the end, you will just feed all those values into a convolutional neural network, which will combine those different patterns that have been found within the image and combine them in a nonlinear way, just like a conventional artificial neural network is doing, and then give you at the end a prediction Y, an output Y that will tell you whether the cat is here. So all the end, this is going to be the part that is the traditional fully connected neural network. So this part is exactly similar to an artificial neural network. So this one is the easy part because we have seen this part already. Now what we need to focus on is the part that comes before this. So you will have a certain number of operations that we need to review that are specific to convolutional neural network. The first thing that is going to be a key operation is some convolution. So this is, as the name suggests, the CNN, the C stands for convolution. So this is going to be an important, maybe the most important operation of a CNN. So the goal of this convolution will be to detect certain patterns in the image. So this pattern can be a shape, it can be a line, or any kind of relevant pattern that will be useful into helping us detect whether there is a cat or not. So we'll come back to this in the next slide to see more about what this convolution operation is. The second type of operation will be the activation. So this is going to be in the same way as you have the activation in an artificial neural network. So this is the same thing here. If certain patterns are found within the network, they are going to be activated and transmitted to the following layer. So this is going to be the activation step, and it's pretty similar to the activation in an artificial neural network. So we will come back to that as well. And the last type of operation that will be also pretty important is the pooling operation. So the goal of the pooling operation will be to simplify the image. So here the goal would be to reduce the number of parameters to avoid having a model that is too complex by finding some ways to simplify a complex image into something more simple, to simplify the representation of this image. So you will have a combination of those convolution, activation, pooling, etc. And those things can be repeated several times. So you will have different layers. So maybe layer 1, layer 2, layer 3, etc. So you will have one after each other, different types of those operations that is going to transform the image into something else, and this information will be transmitted little by little and eventually will be transmitted to the fully connected artificial neural network at the end of the CNN model. So let's see an example of what a convolutional is. So for this, let's take an example of we take a given image made of certain pixels, and each of those pixels will have a given color or a given luminosity based on the value of each pixels. And based on this, our goal here will be to look at these pictures and detect whether there might be a pattern that suggests that there might be a crack that is visible on this picture. So let's assume that this is a picture of a piece of concrete, and we want to be able to detect whether there is a signature of a crack within this piece of concrete. So now let's assume that each pixels can have a given value. Let's assume that in this case it's just a black and white picture, and the value of the pixel can vary between -1 to +1, where -1 means that the pixel is fully white and +1 means that the pixel is fully black. So in this case, this is what the computer sees, just a collection of points of pixels, and for each pixel one value that can go between -1 or +1. And the goal of this is to, starting from there, to detect whether there might be a pattern suggestive of a crack within this picture or not. So if you look at this picture as a human, then it's pretty obvious that there is a black line in the middle of this picture, and that this black line might be a crack, that you have a vertical crack that is going through the middle of these pictures. But again, the question is, if you want to train a computer to detect such cracks, how will you do that in practice? Because cracks can be anywhere, so you cannot just detect a crack by looking at a given pixel and saying, is this pixel equal to +1 or -1? Like you can have the same crack, but depending on how you take this picture, maybe the crack will be in the middle or the crack will be on the edges. So each pixel can be equal to +1 or -1 independently of whether there is a crack or not. So you cannot use those kind of simple rules to look at the different values of each of the pixels individually to say whether there is a crack or not. And also, if you look at this, then you won't necessarily be aware as to whether those black pixels that are +1, are they next to each other? So that if you have some pixels that are next to each other, then it suggests that they are forming a pattern together. They might be forming a big crack. But if you just look at those pixels one by one, then you don't have necessarily the information as whether those pixels are connected to each other. So the convolution operation will consist in starting from this picture here, will consist in doing a convolution operation. So we'll come back about what a convolution means, but we are going to write it like this. This is going to be the symbol of a convolution. So we're going to start with this grid here, and we are going to convolute it with another grid, typically a smaller grid. For example, in this case, we're doing a 3 by 3 grid, so something like this. And this grid will also come with its own values for each of the pixels of this grid. So for example, in this case, we're going to put some 1s here, some 0s in the middle, and some -1 on the right. So this is going to be what we call a filter. And so the convolution operation consists in starting from your initial image, convoluting this image with a filter, and this operation will give you a new grid, a new output grid in return. So now let's see what this convolution operation means. So the way the convolution operation is going to work is that you are going to place the 3 by 3 filter on top of the image, the input image. So you're going to place the filter like this, and then you are going to multiply pixel by pixel the value of the pixel of the image times the value of the pixel in the filter, position by position, so box by box. So in this case, in the case of this first example, you are going to do this pixel here -1 times this one times 1, -1 times 0, -1 times -1, etc. So you're going to do member by member, multiplying the pixel of the filter by the pixel of the image, and after multiplying those elements, you are going to sum them all. So you're going to do -1 times 1 plus -1 times 0 plus -1 times -1 plus -1 times 1 plus -1 times 0, etc. So in this case, for this first position for the filter, you will have -1 times 1 plus -1 times 0 plus -1 times -1 plus -1 times 1 plus -1 times 0 plus minus 1 times minus 1 plus minus 1 times 1 plus minus 1 times 0 plus minus 1 times minus 1. So this is going to give you at the end, in this case, 0. So why is it going to give you 0? Because you have 3 minus 1 that you are multiplying times 1, so that's going to give you minus 3. Then you have minus 3 times 0, that's going to give you 0. And then you have minus 3 minus 1 times minus 1, that's going to give you plus 3. So you have minus 3 plus 3, so that's going to give you 0. So in this case, it comes from the fact that this filter has as many plus 1 as it has negative 1. So it means that if the image within this filter always have the same value for the pixel, then the filter will return a value of 0 because you have as many plus 1 as minus 1. So if all the values for all the pixels within the image within the area highlighted by the filter, if all those pixels are the same, then this filter will detect nothing. It will detect that it's equal to, it will give you an output that is equal to 0. So we're going to put the output given by this filter here in this box. So in this case, this is equal to 0. And then what we are going to do is to start moving the filter. So for example, we're going to move the filter down like this, redo this operation. So in this case, it's exactly the same operation because the value of the pixels are all equal to minus 1. So you will get 0 again. Then you will do that one more time, and so if you move the filter here, you will also get 0. So you will have 0 here. Here I'm missing one line in my grid here. So if you continue moving down the filter, so if you move the filter one more time like this, then again you will get minus 1 that you will convolute with the filter, and you will get 0 like this. And then so you will start moving the filter not only up and down, but also you will start moving the filter left and right. So now you will place, for example, your filter here. You started from here, now you will start to move it to the right, and then you will just gradually translate your filter like this. Then you will move it here, 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 here. You will move over all the position within your image. So let's put it here for now, and let's see what is the result that we get. So here, the result that we get when we do the convolution between the image and the filter, so we will get those minus 1, they are going to be multiplied by 1. So we are going to get minus 1 plus minus 1 plus minus 1, which is minus 3. Then we have those 3 pixels here that are going to be equal to 0. They are going to be multiplied by 0. And then you have plus 1 plus 1 plus 1 that are going to be multiplied by minus 1 minus 1 minus 1. So you will get minus 3. So you will get minus 3 plus 0 plus minus 3. So now you will get the result of this convolution operation will be minus 6. That's what you will get. Then if you start moving your filter here, 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 it's just gonna give you the same result over and over. So you will get minus 6, minus 6, minus 6. Now let's see what happens if you move your filter one more step. So you move it here. Now what you get is minus 1, minus 1, minus 1. So minus 3 plus 0 plus minus 3. So you get again minus 6 here. That's going to be exactly the same result. If you move your filter one more time, now you get something different, because now again all the pixels within the image, within the area highlighted by the pixel are the same. They are all plus 1. So again, in this case, you will get 0. You will get plus 3, plus 0, minus 3. It comes from the fact that in this case, all the pixels within this fraction of the image are all the same. So in the filter, since you have the same number of +1 and -1, then the outcome will be 0. And that's going to be the same for all the position, all the up and down position. Then, so let's continue. So now let's move the filter here. Now you will get +1 +1 +1 times 1 1 1. So that's going to give you 3. The one in the middle, they never matter. They are always multiplied by 0. And then you will have -1 times -1 plus -1 times -1 plus -1 times -1. So now you will get 3 plus 0 plus 3. So now that's going to give you +6. So you will get +6 in all the position here of this image. Then, so again, let's finish this. So you will move the filter here. That's going to give you exactly the same result. So +6 +6 +6 +6. And finally, if you move your filter here, then again, now your image is fully filled with -1. The image is fully homogeneous. All the pixels are the same. So that's going to give you 0. Okay, so this is the outcome of the convolution. You move your filter step by step. You gradually translate your filter throughout the entire pictures. And then for each position of the filter, you do a member by member multiplication. You sum them all, you sum up all the result, and that gives you the value that you put in your output grid. So in this case, that is going to give you the output for this convolution operation, not the output of the model, but just the output of this convolution layer. So in this case, so let's try to understand what this filter is doing. So this filter is called a vertical edge detection filter. And the reason it is called like this is that this filter is actually detecting edges within your pictures. So as you can see here, when you if you look at the outcome of the output grid that you get, it is 0 when the image is just fully homogeneous, when all the pixels are the same, all the same color, so there is no edge. It becomes very small or very large every time it detects an edge. And what it means to detect an edge means that okay, so it means that to detecting an edge means that in this case it means that the pixels are not the same on the left and on the right. If you move your filter to an area where now the pixel on the left column are not the same as the pixel on the right column, now the filter will give you either a positive value or a negative value. And the reason that the pixels would not be the same on the left or on the right means that you would have detecting an edge. An edge is when you have some pixels that are black on one side and white on the other side. That's the definition of an edge. So for example, if you put your filter here, you have those pixels that are white, those pixels that are black. And when you do this operation, because of the way this filter is designed, because it put a positive weight on the pixel on the left and a negative weight on the pixel on the right, if the pixel on the left and the pixel on the right are the same, then this filter will give you 0. So there will be no edge detected. But if the pixels on the left and on the right are not the same, then it will detect something and will give you a result, will give you an output that is not 0. So in this case, there's two types of output. If it detects that the pixel on the left are white or are light, then, and if it detects that the picture on the right are dark, so you have a light to dark transition. So this is what happens here. Those pixels are light, those pixels are dark. Then in this case, it's going to give you a negative value. So in this case, it's giving you -6 is the maximum possible values, or the minimum, the maximum in absolute value, or the minimum possible values. This is what happens every time it detects that there is a light to dark transition. When the pixels are light on the left and dark on the right, this filter will give you a negative outcome. And then on the other hand, if you put your filter here, for example, now all of those pixels are dark and they differ from all of those pixels which are light. So now you have a dark to light transition. And then that in this case mean that there is also an edge here. There is an edge. You have a transition from this time dark to light, and in this case that's gonna give you a positive value, which in this case the maximum value. When you have a perfect transition from pure white to pure black, then that's gonna give you a +6. So in this case, that's why this filter is good at detecting vertical edges, because it detects when the value of the pixel is changing between the left and the right. So whenever you are here or here, there is no edge, so it's gonna give you 0. When you are also in the middle of this crack here, that's the same thing. There is no edge, so that's also going to give you 0. But every time you are here at the edges, then this is where it detects that there is the crack. So this is where this is how you will get some features here. It has detected that there is a certain pattern. It has detected that there is a vertical edge, like that you have a transition from dark to light pixel or light to dark pixel. So this suggests that there is a transition between something and something else, maybe transition between the background and a given object, or transition between regular concrete and a crack. And in this case, if you have this kind of vertical transition, then this filter will be able to capture it. So that's an example of filter. In this case, that's a vertical edge filter, but you can think of many other types of filter that once you convolute your image by the filter, it will be able to detect certain types of patterns. So that's the first example of filter. So when you have this vertical edge, here the main idea is that this filter will give you a positive or a negative value, at least a non-zero value, if the pixel on the left are different from the pixel on the right. And if all the pixels are the same, then they will be +1 and will compensate the -1. So the outcome of this filter will just be 0. Then if you want to do now the same thing, but to detect now not vertical edge, but horizontal edges. So this, if you apply this filter to a picture where you have a crack that is not verticals but horizontal, this filter will not work in this case, because it only going to give you a non-zero value when the pixel on the left are different from the pixel on the right, which would not be the case if you have an image like this with a crack like this in the middle. Then you will place your filter like this, and the pixel on the right will be the same as the pixel on the left. So this filter would still give you a 0 value. It won't be able to detect a vertical crack. It won't be able to detect a horizontal crack. It can only detect a vertical crack like this. So if you want to be able to detect a horizontal crack, then you need a filter to detect horizontal edges. And in this case, the idea is exactly the same. So this can be accomplished by a 3x3 filter again. But this time what you will do is, rather than having some +1 on the left and some -1 on the right, you will put the +1 on the top, for example, put some zeros in the middle and some -1 at the bottom. So this idea of the horizontal edge filter is exactly the same as for the vertical edge, except that this time, so still the sum of all those elements is 0, which means that if you apply this filter on a homogeneous part of the picture where all the pixels are the same, this filter will give you a 0 outcome, a 0 output. But if the pixel at the top are different from the pixel at the bottom, then this filter will give you something that is not 0. So it's going to be able to detect some boundaries, some edges between different objects that this time are not vertical, but that are, in this case, horizontal. Another potential example of filter, which is typically not very useful, but if you think about, for example, a filter like this that would entirely be made of +1, what this types of filter would do is to blur the picture. So, for example, to illustrate this better, let's assume that this filter is not made of 1, but it's actually being made of 1/9, 1/9, 1/9, 1/9, etc. So 1/9 in each of the values of this filter. So then when you think about what would happen if you have your image like this, so you have your image made of pixels, then you will put your filter like this, and then what you will do is to take the pixel 1 times 1/9 plus pixel 2 times 1/9 plus pixel 3 times 1/9, and what you will get when you do this is that you will take the average of those 9 pixels, sum them all, and then divide by 9. So what you will do, the outcome of this operation will be to do some kind of moving average or a blurring, where for each pixels, the outcome of this will be a local average of the values of all the pixels. You will sum all the values of all the pixels around these pixels, and then this pixel now will be equal to the average of all the neighboring pixels. So what you will do is that you will take each pixels and convolute it with all its neighbors. So you will replace this pixel by the value of the average of all the neighboring pixels. So this is gonna make the picture more blurry, because now each pixel will now be merged with its neighbor, so everything will become less sharp, more blurry. So that would be, in this case, a blurring filter, which can be useful if you want to, for example, hide the face of a person. You can apply this kind of filter to make the face more blurry, so that we can't see the detail of the face anymore. In general, filters don't have to be equal to 3 by 3. They can have any types of arbitrary values. So you can have, for example, a 2 by 2 filter. And in general, the value of the coefficients within the filter, not only they can be free to have any kind of arbitrary value, so it doesn't have to be 0, 1, -1, etc. So you will have, in this case, for a 2 by 2 filter, you will have 4 different values, 4 different coefficients. And more than this, that's actually going to be the most important thing, is that the CNN will need to learn what is the right coefficient to use for the filter. Here I showed you the example of an intuitive filter, which is a filter to detect a vertical edge or a horizontal edge. But in general, we don't know, for the picture that we want to analyze, we don't know what are the typical patterns that we want to detect. Maybe we want to detect some vertical edge, some horizontal edge, but that's not going to be enough to detect if there is a cat on the picture. Like, we need to be able to detect some more complex patterns. And the way to detect those patterns is that we need to let the model come up on its own with the best possible features that are going to detect the most relevant patterns to detect whether there is a cat or not. So in general, what we will do is that we will just let the filter with 4 weights, and those weights will need to be adjusted by the model. The model will learn how to recognize a cat, and the way it will learn how to recognize a cat is to adjust, to come up with the best possible choices of those weights that will make this model be able to recognize what are the typical features of a cat. So those weights will need to be adjusted. They will be adjusted when the model starts to learn, when the model learn how to recognize a cat. So that's going to be part of the learning of the model. In the same way that in an artificial neural network, the learning of this network consists in tuning the values of the weights and of the bias in order to be able to map correctly the input to the output. Here, the one of the most important ingredients of training the CNN will be to expose this model to several examples of pictures that are cats or not cat, and then based on this, the model will learn how to adjust the value of the coefficients of the filter in order to learn how to predict whether it's a cat or not. And to do this, it needs to learn how to detect the right patterns that are the most influential in determining whether there is a cat or not on this picture. So to summarize what the convolution is doing, so you start with your given input image. So this image is going to be made of a collection of pixels. So for example, it's going to be an n by n pixels. So n by n, where n is the size of the image. So in this case, let's assume that's a square image. So the number of columns is equal to the number of rows. So that's the size of the image. So you will have n by n or n square pixels. Then you are going to do a convolution of this image with the filter. So typically the filter has to be smaller than this image. So the size of the filter will be f by f. So f is going to be the size of the filter. And the result of this will give you an image, a new image, that is going to be slightly smaller. Why? Because you will start by putting your filter here, when you will start to put your filter here, then here, etc. And the number of times you can put the filter within the image is lower than the number of pixels that you have within the image. For example, let's take an example. If you have an image that is a 4 by 4 image like this, then you will convolute it, let's say, with a 2 by 2 filter. Then in this case, you will put your filter here as a first step, then you will put your filter here as a second step, then you will put your filter here as a third step. So this outcome will give you a 3 by 3 image at the end. So if you convolute a 4 by 4 image by a 2 by 2 filter, you will get a 3 by 3 output at the end. So the general formula to relate the size of the image, the size of the filter, to the size of the output grid that you will get is that the size of the output grid will be equal to the size of the image plus minus the size of the filter plus 1, and then you will get this for the height and for the width. So it's easy to understand that if the size of the filter is increasing, then there is a less amount of possibilities for you to place the pixel. If the filter is very large, there is only a few possibilities according to which you can move the filter around. So that's going to give you a smaller output. And if the filter becomes exactly the same as the image, if f is equal to n, then there is only one possibility where the filter just takes the entire space and covers the entire image. And in this case, n minus f would be equal to 0. So you would just get a 1-by-1 output, just a single output, because there is only one way to put the filter. And in general, the more the image is larger than the filter, then the larger will be the output that is generated by this operation. So there is one problem with this, is that in this case, you start with a given image, and the output that will be produced by this convolution operation will become smaller. And it can become potentially very small if you use a very large filter. So that's an issue, because in a typical CNN, you will need several layers of filters, one after the other, which means that every time you apply one filter, the image will shrink. So that's one premise, that at the end your image will become like very small, because you keep reducing its size as you go from one layer to the next. And the second problem is that when you do this, you can never detect very accurately what occur on the edges of your image, because every time, even if you put your layer on the very top left like this, if you apply your filter on the very top left, then it cannot see very well what's occurring on the edges, because it's going to this is going to be merged with the rest of the filter at the other position. So you have a lower weight placed on the edges of your image. On the other hand, the middle of the image, there is plenty of possible position for the filters to be in the middle. So the middle of the image will have a lot of weight, but the edges of the image will have a very low weight, because there is a very limited number of possibilities that you can place the filter on the edges. So you are losing some information. You won't be able to detect some patterns at the edges of your image. So there is one solution for this, which is to use padding. So padding aims to address this problem, to allow to put more weight on the edges, to have the same weight on the edges as you have in the middle of the image. And it's also going to prevent the image from shrinking. So the idea is that if you start from this situation where you start with your 4x4, you convolute it with a 2x2 filter, and you end up with a 3x3 output grid, what you will do to avoid this image to shrink and to avoid having a low weight on the edges is that, since the problem here is that when you have your 2x2 filter, there is only one way that you can put your filter so that it will cover the top left corner here. The top left corner, there's only one possible position for the filter that will overlap with these pixels. So to overcome this, what we will do, we will use padding. And the idea of padding is that you will add some fictitious pixel around your grid like this. You will add a new row and a new line of pixels. So by convention, we will put all those pixels to be all 0 so that they won't play any role. But now, by having those pixels at the edges, now it will put more weight on the edges, because now you will be able to put the filter here, you will be able to put the filter here, you will be able to put the filter here, which means that now you will have 4 possible filter that will be able to overlap with this pixel here. So now it means that this pixel will have exactly the same weight as a pixel in the middle. So now it means that you will be able to have more weight on the edges, and also that's going to avoid the shrinking of the image, because now you will be able to put a first filter here. That's going to be 1, 2, 3, 4, and then 5. So now the result of this will be a 5 by 5 grid. So that's going to become even a larger grid than initially. So now you will start with, so you started with a 4 by 4. So initially that was a 4 by 4 image. After the padding, now you have added 2 lines, 2 extra lines and 2 extra columns. So now it becomes a 6 by 6. You convolute this with the 2 by 2 filter. And at the end, now you get a 5 by 5 output grid. So now the general formula is going to give you the size of the output that you will get. It's still the same idea. So when you have no padding, the size of the outcome is the size of the image minus the size of the filter plus 1, and that's what you will get for the height and the width. So now it's the same, except that now instead of having n, we need to add the size of the padding. So now what we will do is to add another parameter p, which is the padding thickness. So in this case the thickness will be 1 in this case, because we only add 1 layer of padding, but potentially we could add more than 1 layer of padding if we had a very large filter. So in this case it means that now the new size of the pixel of the grid here will be equal to n, so the size of the starting image, plus 2 times the padding, because we add 2 times the padding on the left, on the right, on the top, at the bottom. So now the new size of the image becomes n plus 2p. So what we can do is just reuse the same formula, but replace n by n plus 2p. So now the new output image that you will get will be n plus 2p minus f plus 1. And so you will get this for the height and the width. So you will get n plus 2p minus f plus 1. So which means that depending on the padding that you use, depending on the filter that you use, you can either get an output image that will be smaller or potentially larger than the input image that you had. So that's the role of the padding. It's to avoid the shrinking of the image, but also to put more weight on the edges, and especially to put more weight on the corners that have otherwise a very low weight if you don't use any padding. So now what happens if your starting image, rather than just being black and white, so in this case where each pixel would have just one number depending on how white or how black it is, now what happens if rather it is a colored image? That is to say, if it's a RGB image with 3 channels that indicate the level of red, the level of green, and the level of blue. So now this image has another dimension, which besides the height and besides the width is what is the value of this image for the 3 channels. So one way to look at this image is actually that it's 3 images on top of each other, where each image corresponds to the value of the level of red, the level of green, and the level of blue. So now you have 3 channels within this picture. So potentially you could have more than 3, but typically for like a colored picture, RGB, you have 3 channels. So now instead of having a 4 by 4 image, now you have a 4 by 4 by 3, because now you have a new dimension, which is the channel, and in this case you have 3 channels. So it's increase the number of pixel values by a factor 3 in this case. So now what happens is that when you will do a convolution with this, now your layer will need to have the same dimension. So now your layer, instead of being, for example, a 2 by 2 filter, now it will need to be a 2 by 2 by 3. So now you will need to add the same kind of thickness, the same kind of channels within your filter. After this, the operation will still be the same. Now the main difference is that rather than being a two-dimensional object, your filter now becomes actually a three-dimensional object. So now it becomes like some kind of small cube like this. And what you will do is that you will place your small cube like this, and you will start doing the convolution operation, and then you will start moving this cube around in your image, and you will do exactly the same. But rather than just doing this in 2 dimensions, now you will do it in 3 dimensions. So what you will do is that you will take this pixel times this pixel plus this pixels times this pixel plus this pixel times this pixel plus this pixel times this pixel plus this pixel here times this pixel here plus this pixel here times this picture here plus this pixel here times this pixel here, this pixel here times this pixel here, etc., etc. So you will take all the value times this pixel here times this pixel here and this pixel here times this pixel here, etc. So you will still do the same, but rather than doing it in 2D, you will do it in 3D. You will still take element by element, pixel by pixel. You will multiply the pixel of your input image by the pixel of the filter, and then you will sum them all. So at the end, you will get an output that will not be 3-dimensional anymore. Now it's going to be only 2-dimensional, because for this first position of the filter, you will get one number. Then you will move the filter to a new position like this, and you will get another value here. Then you will move your filter to the last position here. You will get a new values. Then you will start to move your filter down, and you will get 9 values. But in this case, the output that you get is not 3-dimensional anymore, because you have multiplied the pixels of your input image times the pixel of your filter image, and then you would have sum all the result over the 3 channels, and that gives you only one single number. So at the end, your output has only one channel. It doesn't have the 3 channels of the starting image. So the main interest of this is that now, so you can apply these techniques of the filter on images that are not just in black and white. You can apply it to colored images that have 3 channels. And also it means that here your filter now has an extra dimension, which means that the filters, the parameters of the filter don't have to be the same for red, green, and blue, which means that, for example, if you use a vertical edge filter, you could apply the vertical edge only on the red, but not applying it on the green or on the blue. Or you could apply this vertical edge on all the 3 colors, or you can apply one vertical edge on the red, one horizontal edge detector on the green. So now you have more degrees of freedom. You can analyze more features of the image color by color, and applying at the same time different filters on each of the 3 colors, and combine all of those results all together. So that gives you more freedom, because you can apply different types of operation at the same time on each of the 3 channels of the image. So now, based on this, let's see what would be an example of one layer within the network. So the network will be made of potentially a lot of layers, but let's see one example of layer. Let's talk about the first possible layer that you will get. So in this case, you will start with your input pictures, which in this case we are just going to say that this picture is just in black and white, so that there is no channel, or only one channel. And then so you are going to convolute this image by some filters. So far we have seen an example where you have only one filter, but in real CNNs, in each layer, just like in artificial neural network, you have several neurons per layer. In this case, you will also have several filters per layer. Why? Because for starting from your initial image, you cannot only detect the vertical edge and then move to the next thing, because you will have lost all the information of the image. As long as there is no vertical edge, this filter will give you something that is close to 0. So you will have lost all this information. So you need to have on the same layer several filters, like a lot of filters, a certain number of filters, and each of those filters will detect something different that is going to be useful. So you will have certain filters that will detect vertical edges, certain filters that will detect horizontal edges, or other types of features that are going to be useful. And all of those filters will be in parallel to each other, just like the different neurons that a given layer is made of. So you will have, let's assume for example that you have two filters. So you will take this image and convolute it with two different filters. So filter 1 and filter 2. So in this case, just to make it clear, so let's take an example where so that we can track the dimension of this image. So let's assume that you start by a 4 by 4 image like this. So you will convolute it with two distinct filters, and let's assume that one is going to be detecting a 3 by 3 vertical edge detector, and another one will be a 3 by 3 horizontal edge detector. So that's in this case, this is going to be filter 1, and you will have filter 2, and those two are in the same layer. This is your input image in this case. And in this case, so the role of those two filters will be to detect the vertical edges and the horizontal edges as a simple case. So then once you do the convolution, what you will get is the new output grid. So in this case, if we don't use any padding, so you start with a 4 by 4, you convolute it with a 3 by 3. So in this case, the result will be a 2 by 2 output image. So this 2 by 2 output image will contain whether an edge has been detected or not for each of the possible position of the filter. And then the next step is the step of the activation. So what you will do in this very same way that you have in an activation a neural network, an artificial neural network, what you will do is that you will start with this output image here. You will add a bias. So when I say add a bias, I mean that you will add a constant number to all the values of each of this grid. And then you will subject this grid to an activation function, a nonlinear activation function, A, for example, where this activation function can be a sigmoid, can be a rectified linear unit, a ReLU function, or an hyperbolic tangent, or something else that is going to be the nonlinear activation function. So in this case, what you will do is that this is going to be the output from the convolution between the input image and the filter. You will add the bias. So this will be equivalent to, in the artificial neural network, this step is equivalent to when you combine all the neurons from the previous layer. You combine them, you sum all of them together with some weights. Here the weights corresponds to the value of the filter. You add the bias. So this corresponds to the quantity z that we saw in the artificial neural network. And then you feed this value z to the activation function, where the activation function, for example, can be the ReLU function, which is equal to 0 when z is negative, and then is equal to z when z is positive. So that's the ReLU activation function. And then, so this, what you will do is that you will take each of the pixels of this grid, you will add the bias, and then you will calculate the value after taking the activation function. You will apply the activation function of each of the bias, of each of the pixels, sorry. So you will do this pixel by pixel. So in this case, the size of this grid will not change. You will do it pixel by pixel. Pixel by pixels, you will add the bias and then apply the ReLU activation function. That's going to give you this pixel. Then you will do it for this pixel. You will add the bias, apply the activation function, and that's going to give you this pixel, etc. So that's going to give you, in this case, a 2 by 2 grid. It's not going to change the size of the grid. So now, now that you have this, so this is the step of the activation. So now we have the step here of the convolution, and we are going to combine the convolution with an activation. So if you think about this, this is very similar to the different types of operation that you have in an artificial neural network. In an artificial neural network, you have the input neurons like this, plus the bias. And then what you have in a neuron is that first you will take all of this, you will sum them all with some given weights, and then you will feed that to your activation function, like for example the ReLU, and this is what is going to give you the output. So this is what you have. This is a neuron in an artificial neural network. So here it's exactly the same idea. You start with your input, so those are the equivalent to the input neurons. Then, based on the filter, you are going to sum all the inputs, multiply them by some weights, which are the coefficient of this filter, and you will add the bias. So this is going to give you a quantity z, which is the output here, the result of the convolution operation plus the bias. This is going to give you exactly the same thing as this. This is when you sum all the neurons, add the bias, and the neurons are summed with their weights, and that gives you the output, which is the value z. And then you will apply the activation function to z, and this is what is going to be the output of the neuron. Here this is the same. You create z by starting from the output, doing the convolution operation by multiplying with some weights in the same way that you multiply with some weights here. That gives you z. You fit that to the activation, the nonlinear activation function, like the ReLU, for example, and at the end what you get is the same thing as what you would get within an artificial neural network. Now the network has combined all the features, all the values of the pixels to create a new features that is going to be useful for the next layer. So here it's the same idea. Each of those filters, they are going to detect different patterns. If those patterns are detected in a satisfactory fashion, then they are going to be activating this function. So this is going to be equivalent to a neuron that becomes activated, which means that the signal is going to be transmitted. So now you will have a new feature that is going to be activated if a certain types of pattern has been identified by the filter. And if the filter has not detected anything, then it's not going to be activated, and this is just going to be 0 in this case. So in this case, like each of those new grids corresponds to a new feature that is going to be transmitted to the rest of the network if this feature, if this pattern has been detected in the image somewhere. So the main advantage here is that now the outcome, like this feature, will be transmitted like it doesn't matter where this pattern has been detected. It can be detected anywhere. Like it's still going to be transmitted through this network. So the where the information is, where the pattern is, that doesn't matter, like because you apply the same filter everywhere on this picture. So that that's why you can use a smaller number of weights, because you don't have to apply the same different weights to different pixels. You can just define one filter and then gradually move this filter. And the other advantage of this approach is that you can use pretty small filter, which means that if you think about this as being your output neurons, here this is the input neurons, now this is here the output neurons, and here the neurons are not all connected to each other, because every time you apply the filter, so for example, to calculate the value of this output neuron, you will only place your filter like this, which means that this neuron here will be only connected to those 9 neurons. So it's not going to be connected to all the neurons. You will have a smaller number of connection. So this is by using some small filters like this, you decrease the number of connection, and this is what allows you to have a lower amount of weights, a lower amount of parameter that needs to be fixed than what you would have in a fully connected artificial neural network, where all the neurons are connected to all the neurons of the following layers. Here, each box like this is only going to be connected to a limited number of boxes. It's not going to be connected to all the pixels within your image. So at the end of this layer, what you get in this case is 2 grid like this. The last thing that you will do to finish this layer is that you will combine those 2 grids, you will stack them up on top of each other, and you will transform them into 2 grids that are on top of each other like this. So you will transform it into a new image that now has 2 channels. And the main interest of doing this is that now you have created a new fictitious image. So it's not a real image anymore. Now it's just the outcome of your convolution analysis. So the value of each of those pixels here will correspond to whether or not certain patterns have been activated or not, whether some horizontal edges have been detected, and whether some vertical edges have been detected. And so each of those pixels will now contain this information, whether each of the filters have detected something. So now you get 2 channels. It corresponds to the fact that we used 2 filters. The result of those 2 filters is stacked on top of each other. So the two channels come from the fact that we used 2 filters. So each of the channel will correspond to the outcome of one distinct filter. And the main idea is that now you get a new grid, and this grid has exactly the same format as the input image, except that now it has a different size and a different number of channels, but it can be used as input for the next layer. So now you have recreated a new grid that will be used as input for some new filters, so for a new convolution operation, for a new activation, and it's going to be the beginning of the next layer. And you can have several layers, one after the other like this, where every time you transform the input image into another grid, and this grid is going to be transformed again into another grid, etc. And every time the more filters you have, the more channels you have at the end of the output grid that you will be generating for each of the layer of your network. So far we have been talking about the convolution, we have been talking about the activation. So there is an additional ingredients of CNNs that we haven't talked about yet, which is the pooling, and especially the operation that is the most commonly used is the max pooling. So as we said in the beginning, the role of the pooling is probably much more simple to understand than the convolution, because in this case the role is just going to be able to decrease the size of the image, to reduce the complexity, to increase the simplicity, to make the representation more simple. So in this case, this max pooling operation, what it will do is that you will start with a given grid. So let's assume that you start, for example, by a 4x4 grid like this. So this grid is, let's assume that it's going to be filled with some zeros here and 1, 1, 0, etc. So let's assume that there is a crack here, for example. So whenever you have a 1, it means that there is a crack. It's a black pixel, and the rest are some zeros, like either gray or white pixels. So in this case, the max pooling operation, what it will do is that it will reduce the number of pixels. It will reduce the complexity. So why? Because in many cases, if you start with a very high definition pictures, you don't need to have so many pixels in order to start analyzing whether there are certain types of patterns, whether there's some edges. And the more pixels you have, the more you will have to, it's going to be complicated to train your CNN models, because you will have more weights, more connections that you need to define. So in those cases, it's very often going to be useful to decrease the size of the image. So this can be achieved by the max pooling operation. So for example, if you do a 2x2 max pooling, what you will do in practice is that you will cut your image into 2x2 little squares. So you will take here, so this is going to be your first quadrant, your first 2x2 quadrant. Then you will take, this time you will not move this like a filter, you will just cut your image into 2x2 segments. And so you will do this for this one like this, and same thing. So you will just do, you will just cut your image into portions of 2x2 groups of pixels. And then the simple thing that you will do is that for each of those quadrants here, you will look at what is the max value of the pixels within those groups. So you will look at, for example, here, for the red position, in this case, the maximum value of the pixel, they are all equal to 0, so it's going to be equal to 0. Then you will look at here, the maximum value will be equal to 1. Then you will look at here, the maximum value is just 0. And here, you look at here, the maximum value is also equal to 1. So what the max pooling does is that it breaks down the image into groups of pixels, and it looks like whether something has been detected or not. It just looks at the maximum value. So this max pooling operation typically comes after a convolution operation. So you have your convolution operation first. It's going to create an output image that will correspond to whether certain types of patterns have been detected or not. And if they have been detected, what the max pooling will do is reduce the size of the grid. It will just look at each of the pixels within one group like this, and it will look like what is the maximum value. So has this patterns been detected or not? In this case, it's always 0, so nothing has been detected. So it's just going to be 0. And then it will look at this group here. In this case, something has been detected. So if at least one pixel of this group suggests that something has been detected, then this is going to be detected by the max pooling. So now what you will get at the end is that in this case there has been two groups of pixels where a crack potentially has been detected. So this one here and this one here. So that's why you have the two value of 1 here. But the main advantage of this is that now you have a much more simple representation of whether some features have been detected or not. So you have lots of information because now you don't know exactly at which pixel those features have been detected, but still now you know that somewhere on the top right and somewhere on the bottom right something has been detected. So you have lost a little bit of information because you don't know the details of where it was detected, but you know that something has been detected at the top right, and in many cases this information is already useful enough. And the main advantage in addition to that is that rather than having a 4x4 grid, now after the max pooling, now you have a 2x2 grid. So you have decreased the resolution, and you have decreased the resolution quite significantly because now the resolution, instead of being made of 16 pixels, now you have only 4 pixels. So the resolution has been decreased by a factor 4. So you have a grid that is 4 times smaller in terms of number of pixels as compared to the input that you're starting with. So the main idea is that now you will be able to use this trimmed version of the grid as a starting point for the new following layer. So you will have decreased the size of the grid, which will allow you to decrease the number of parameters. So that's going to decrease the number of degrees of freedom, the number of parameters that needs to be fixed during the training of the model. So the less parameter you have, the more simple your model becomes. So you have less risk of overfitting, so which is always a good thing. Of course, you cannot just pool you cannot do max pooling after max pooling. That you will just decrease the size of your image so much that you will lose too much information. But if you just use a little bit of max pooling after each layer, then you will be able to reduce the size of your model, make it more efficient, decrease the number of weights to decrease the risk of overfitting without losing too much important information. So that's an important ingredient of convolutional neural networks, because it reduces the risk of overfitting and makes the training of the model more efficient. So now let's see how all those pieces are connected to each other, like the convolution, the pooling, and the final fully connected layer. So typically in a given CNN architecture, so each CNN might have a different architecture, of course, but the general shape will usually look like this. So you will start with your initial image, which will be usually a large image, but with very few number of channels. Either one channel if it's a black and white, like a grayscale image, or maybe 3 channels if it's a colored image. Then the first thing that you will do is that you will apply some filters. So for example, let's assume that you will start by applying let's say 3 filters. So probably typically you wouldn't want to do more than this, but just for the sake of the example, let's assume that you will apply 3 filters. So when you apply the filters, if you don't apply any padding, you will get a slightly decreased size of the grid. Now you have 3 filters, so it's going to give you 3 different channels like this. Then what you are going to do is, to avoid having too many coefficients, you will apply a max pooling. So for example, a 2x2 max pooling, which is going to reduce the size of the image, but keep the same number of channels. Then after this, you may want to apply some new filters again. So this time maybe you will apply more filters to detect more advanced features. So maybe you will use this times 5 filters. So you will get some new grids like this. This time you will get 5 grid after the application of those 5 filters. Again, you may want to do a max pooling at the end to reduce the size of the image that you get. So you will get your 5 layers like this. And then what you will do is that, so you will restart from there, and now you will flatten the different grids. So let's assume that at the end here, let's assume that you had some 2 by 2, where 2 by 2 is the size of the grid, times 5, where 5 is the number of channels that you have. Now it means that you have 2 by 2, 4 equal 20 different values for the pixel. So now what you will do is that you will flatten this and transform this into a 20 by 1 vector. So a vector with just 20 different elements like this, and this is going to become now the input layer for a fully connected artificial neural network, where you will have now some hidden neurons like this that are going to be connected to your input layer like this, and that are going to be connected maybe to some other hidden layer like this, which eventually is going to be connected with the output layer. So you will have the output here, the final output of your model. Here, this is going to be the hidden layer of your fully connected neural network. So if we summarize, you start with your given input image, then you will subject it to some filters and to some pooling, and usually a group of 1 filter plus 1 pooling. This is what we will call 1 layer. So here you would have 2 layers in this case, one first layer with the 3 filters, then a second layer with the 5 filter, and then after those 2 layers, after the first layer and the second layer, now you will move to the fully connected artificial neural network, which is going to combine those different features, combine them together in the same way that an artificial neural network would combine the inputs of the network, and eventually it's going to give you the output y. And as a reminder, in this case, if y is larger than 0.5, then it means that a cat has been detected. If y is lower than 0.5, then there is no cat, or no crack, or no whatever the pattern, whatever the objects that you are trying to detect in this case. So the main objective of this types of network usually is that initially you will have some low-level filters that will try to detect some low-level features, like detecting some edges, detecting some shapes, simple things, simple patterns that you can find within the picture. And then those features themselves, those simple edges, those lines, those shapes, are going to be themselves combined with each other within some more advanced filters that will combine them to each other to find some more complex shapes, some more complex patterns. For example, in the case, if you think of a cat, maybe if you want to find a signature of the eyes of the cat, then you will need to find 2 circles which would correspond to the 2 eyes of the cat. So maybe you will need one low-level filter that will detect the eyes of the cat, and then you will need a second more higher level filter that will detect that now you have 2 eyes that are at a given certain distance from each other and that are horizontal with respect to each other. So that would be an example of a higher level filter that will rely not on the initial picture but on a grid that would just have detected that there is 2 eyes. So for example, starting from the cat here, you will have the one of the filter here will have been, for example, will have detected two eyes like this, and maybe one of the filter here will detect that you have those two eyes, so it will detect that those two eyes are forming the shape of a typical face of a cat. So as you go deeper and deeper within your network, you will be able to combine all the low-level features like the lines, the shape, the edges that you have detected, and combine them into trying to detect some more complex patterns describing the objects or the animal that you are trying to detect within the input image. And then at the end, you will combine all those features together, and those features, depending on whether those features have been detected or not, it's going to activate or not the neurons. And at the end, your given output, depending on whether it has been activated enough or not, if there is enough signature of a cat, or if there's not enough signature of a cat, then your model will predict whether it is a cat or not a cat. So that's going to be the main idea of an artificial, a convolutional neural network. So now if we think about how we're going to train this thing. So far we haven't talked so much about the training. So now let's see what are going to be the elements that needs to be trained. So the first thing that you will need to do when you will be training, so by training I mean that you will provide a lot of pictures to this CNN. In some of the pictures you will have a cat, so in this case you expect your model to give you y equal 1. That's the perfect answer that your cat should be giving you, that your network should be giving you if there is a cat. And you will also provide some examples of pictures where it's not a cat, it's something else that is clearly not a cat. So in this case, you expect your model to give you y equals 0. That is to say, it should be able to predict that it's not a cat. So you will provide a lot of examples of pictures where it's cat or no cat, and you will train your model to give you the right answer, to give you the answer that you expect. And the model will learn by trying to adjust the weight so that it can predict properly the image that you give the model as a training set. So the way the model is going to learn is to change the value of the coefficients that are free to change, the weights, the coefficients. So the first thing that is going to change is the filter. So here, every time you have a filter, you have some weights, and those filters, they are not predefined. You don't know yet what are the typical features that you want to find. So the weights of each of the filters is something that is going to be changing during the training. So here you have some filter here, you have a second set of 5 filters here. Those, they need to be trained. What doesn't need to be trained is the pooling. The pooling is just doing a simple mathematical operation, which is to take the maximum of a group of pixels. So here there is no training required for the pooling. There's just nothing that needs to be trained here. And then the second thing that needs to be trained will be the fully connected neural network. Every time you have some connection, you have some weight, you have some bias. So those weights, those bias will need to be trained as well, in the same way that you train a typical artificial neural network. So this is going to be the last step of the CNN, is that after you have decided the architecture, then you will need to train this model. So to summarize what you will need to do for training a CNN model, the first thing that you will need to do even before the training is to decide the hyperparameters. So the hyperparameters are the parameters that defines the architecture of your model, and those parameters, they are not trained. Those are fixed parameters that you need to choose, that will define the complexity. So in this case, the hyperparameters for a CNN will be the number of layers, the number of times you do a convolution, a max pooling, etc., and the number of filters as well, the number of filters that you apply on each of the layers, the size of the filters, whether you are going to do some filter of 2x2, 3x3, 4x4, etc. So those are all parameters that are not going to change during the training of the model. Those are hyperparameters that you need to decide at the beginning which value you should be using for this. Same thing, the architecture of the fully connected neural network at the end, like in the same way that you have for a regular ANN, you need to decide the architecture, like the number of layers, the number of neurons per layer. So all those things are things that are not going to be trained. So those are the hyperparameters. It needs to be decided at the beginning, and you need to choose wisely the value of those parameters to avoid having a model that is too simple, that would be underfitted, or a model that would be too complex, that would be overfitted. So at this point, it starts to be very, very hard to find the right value of those hyperparameters, because there is so much hyperparameter and they can all play a role. It's not like in Lasso when you have only the regularization parameter that you need to change, or in a simple ANN with a single in a single hidden layer, then you have only the number of neurons that you have in the hidden layer that can change. Now you have really a lot of hyperparameter that needs to be tuned, so it starts to be pretty difficult to find the most optimal values of those hyperparameters. So this is where it will start to be very useful to have some experience, but very often for CNNs, what you would do is that rather than trying to find on your own the most optimal values for the hyperparameters, you will just use previous values from previous models that have been trained, some models that are pretty similar to your previous example, or you will rely on your own experience, your own intuition. You will look at previous papers or previous work from people who spend some time tuning the hyperparameters, and you will just reuse the same parameters. And then after that, if it doesn't work, then you can start tuning a little bit the hyperparameters, like increasing the size of the filter, increasing the number of the layers, or decreasing the number of layers, decreasing the number of filters. So you can do some small variation and see if that helps your model or not. But it's very hard to start from scratch if you don't know what's the right value for the hyperparameters. It's just more efficient usually to start with some previous architecture that you found from another person and just reuse it and see if it works or if it needs to be improved. So those are the parameters that are not trained. They need to be defined. They are going to define the complexity of your model. Then you will have the parameters that need to be trained. So those parameters, as we just said, those are going to be the parameters in the filters, in all the filters, whether you are going to detect some edges, horizontal edges, vertical edges, or something else. This depends on the parameters in the filter. So those parameters are free to change. They are going to be changed during the training so that your model detects useful patterns, useful features. And then you have the weight and the bias in the final fully connected network. So those weight and bias are going to be trained just like in a typical ANN. And so how are you going to train those parameters? That is going to be the same as a regular artificial neural network. You will need to define a cost function. So this cost function is going to be the error of your model based on the output of your model minus the square difference between the output of your model and the output that you were expecting your model to give you. For example, like if you use the mean square error as a cost function, but there is some other possibilities for this. And then so you will have your cost function j, and the goal will be to minimize the cost function j, and you will minimize j by adjusting the different weights. So you will adjust all the weights, all the parameters, so as to minimize the error of your model, to minimize j. So what you will do is that you will take all your training examples, you will calculate the cost function of your model based on certain some target values for the parameters. You will see if your model is predicting a high error or not, and then you can train your model. You can start to adjust the weights of your model to decrease the cost function. And for example, you can use this by the same method, like for example by gradient descent, by calculating the gradient of the derivative of the cost function with respect to each of the weights one by one. And then if the cost function is increasing with respect to a given weight, then it means that this weight needs to be decreased so that the cost function will decrease. Or if the slope is negative, then it means that the weight actually needs to be increased to decrease the value of the cost function. So you will calculate the gradient of the cost function with respect to all the weights, and then you will adjust, you will slightly increase or slightly decrease the weights based on your learning rates to minimize the cost function as much as possible. So you will calculate the gradient, and then you will adjust the value of the parameters in the direction of the negative gradients to always go in the direction that minimizes the cost function, in the direction of the negative weight. And then you will repeat that several times to adjust little by little the value of the parameters. And then you will recalculate, after having put the new parameters, you will recalculate the value of the cost function, recalculate the gradient to define how you should change the weights next. And you will do this until you reach a satisfactory minimum in your cost function, which means that your model at this point has learned how to get the right values for the parameters, which in this case would mean that it has learned on how to find the best filters, the filters that creates features that are the most relevant, some patterns that are relevant into finding the objects that you are trying to find in your pictures. So this depends on the types of problem that you are dealing with. So sometimes you will want to detect more lines, sometimes you will want to detect more circles or other types of maybe a square or something like this. So depending on the type of problem, you will need to train the filters, and the filters will give you different useful information about your pictures. And then at the end, you need to train the final fully connected network that will give you the final output to tell you if there is a cat or not, if there is a car or not, if there is a traffic light or not, if it's a red or a green traffic light. So by this, you will just adjust all those parameters to minimize the cost function. And once the cost function has been minimized, then you can assume that your parameters are reasonable, so that your model can be used for new pictures, and for new pictures that the model has never seen before. It can take those pictures as input and tell you whether there is a cat or not on this picture. So it can be used to make some predictions based on the pictures it has learned from. It's going to be able to predict in new features, in new pictures, whether there is a cat or not. The idea is that it will have learned how to recognize a cat by detecting what are the relevant features that describe a cat, what is the typical signature of a cat. So it has learned how to generalize what a cat is and to recognize a cat in future pictures.